First, we need to identify where is the problem. Everybody splits files vertically. We need to slice them horizontally across a bit stream, and we need to do it in a very special way in which we will produce, for example, 4 fragments where each bit of each fragment contains 25% of information of every bit from the original file. Here, as you can see, we are splitting the original file of size 1 GB into 4 fragments of sizes 250 MB each. But the amazing thing is that we can inflate those 250 MB fragments into 1 GB files later and XOR them together, producing the original file again. And not only that, but the binary fission operation is also ambiguous, meaning that every time we apply binary fission, it will produce a completely differently looking set of fragments. Now you may think, well, this is nonsense. How on earth are we going to slice one bit of information into 4 pieces? There is no such thing like a 1/4 of a bit, because information stored in 1 bit is either 0 or 1, true or false. It is indivisible. But that assumption is obviously wrong. I'm going to walk you through the binary fission process step by step right now. We can describe it as a card game. Imagine a deck of cards in which there are cards of 4 different types. We have singles, pairs, tuples or triplets, and extras. Each card has a name and there are some numbers written on them in brackets. We have 2 special extra cards here. Joker, denoted as J, which we are certainly never going to use, and null card, which you simply don't want to touch because if you draw the null card, it means you have lost the game. And here are the rules of the game. Imagine a binary casino. As soon as you enter the casino, you realize there are tables of different colors lined up in columns. A croupier will invite you and ask you to pick a color. Let's say you will select the blue one. Croupier will then initialize the counters on a big screen in front of tables and he will ask you to select a random number from 0 to 255. Let's say you have selected 72. He will write down your name as a player blue72 and he will walk you to the first table. You can right away see there are these cards placed on the table: O, P, Q and R. The croupier is going to take the first move and he pseudo-randomly selects card Q. Since there is nothing for you to choose on the card, there is only one number, the number 2. The round is already over. The croupier will write Q2 into the logbook and at the same time he will update the counters on a big screen. Because you were forced to select number 2, which means you want to protect this counter, he will add 3 to the counter 2 and he will subtract 1 from counters 0, 1 and 3. So the total sum of all counters doesn't change. After that, he will walk you to the second table. There he selects the card capital U like Utah. Now the situation is different because there are 3 numbers written on that card, but you can select only one of them. Let's suppose that you have selected number 3. Croupier writes down the outcome of the second round, he puts U3 into the logbook, then he updates counters by decreasing counters number 0, 1 and 2, and by increasing counter number 3, and he walks you to the last blue table. There he selects card D, you select number 2, he writes D2 into the logbook, and then he updates the counters. Since this is the last table, we can start another loop by moving back to the first table. The croupier selects card O. You have no other option but to select number 0, so the round's result is O0. After that, the system updates the counters as usual. Afterwards, you proceed to the second table, croupier selects card V, you choose number 0, and so on and so on. The game may continue as long as you will keep all counters floating above 0, but unfortunately, as soon as one of those counters reaches 0, you will lose the game. The same applies if the croupier selects the null card. Fortunately for us, we do not have a null card on any table, but for a moment imagine there are null cards. If the croupier pseudo-randomly selects the null card, then the game is lost. At this moment, you may argue that this is unfair. Nobody can control this thing. You are going to lose after a few moves anyway, but that is not accurate. There is one magical trick you can pull out and nobody is aware you can do it. You can move back through the time, for example 2, 3, 5 rounds to the past and change your selections there. By doing so, it will affect the present time. Most likely, it will change what is happening right now. And if not, you can rewind time back even more and play the game like this 1,000 times until you get the outcome you want. Isn't that amazing? But there is much more to it. Let's say that you have played the game for several millions of rounds. Nobody understands how it's possible you have survived for that long. But everybody is happy that you are leaving. As a winning prize, you will get the transcript of a gameplay, and here is the code table showing how you can easily transform the transcript into a binary stream. For Q2, there is no need to write anything. For U3, we need to write 1 and 1. For D2, we need to write just binary 0. In case of O0, there is no need to write anything, and the V0 is written as 2 binary zeros. Of course, in case of a transcript containing millions or billions of rounds, we can find a better compression setup for tuples, because as you can see, S0, T1, U2, and V3 are compressed as a 1-bit and other tuples as 2-bit values. But it can happen that S3 is by far the most used selection in the gameplay, and it would be wise to encode S3 as 1-bit value. For that, we have an extra byte called TCS, Tuple Compression Setup. The TCS ensures that the compression of tuples is optimal. Here we have it in a diagram, the entire game's mechanics shown in one simple picture. The process of binary fission relies on this repeating procedure. First, we choose some starting text, which in our case is a declaration of freedom of speech and freedom of data sharing. Then we add the name of the player as a postfix, for example, Blue72. All of this is written into the header of the output file and we can start the game. Before the very first round begins, we initialize the hashing algorithm, which effectively acts as a croupier and converts the entire text into one big number. Let's say, in this case, the number computed by the hash algorithm is 180,230,146. We then divide the number by the number of cards on the table and compute the remainder after the division. 180,230,146 modulo 4 is 2. Therefore, the card with an index 2 is selected and we can choose a number on it. Once the number is chosen, it is written to the game log and as well to the binary output. After that, the hash is updated, the next number pops out, and we go round and round like this for as many times as we want to. Once the last round is finished, we will close the output file. Unfortunately, it often happens that the last bit is somewhere in the middle of a byte, so we fill in the remaining bits with zeros and finally write TCS byte and total count of rounds. The main thing is that the resulting binary file can then be converted back into the game log and anybody can easily verify that the game was played properly. If we try to run this check on a regular file, for example some video in MP4 format or text file, the verification algorithm will fail almost immediately. Either the counters will reach 0 or null card will pop up. There is no chance that anybody will be able to create a meaningful file larger than 8 bytes, which can pass this test without knowing the rules of the game. And since the game starts with the declaration of freedom of speech and explicit statement saying that the file is free and redistributable, and because we know that every bit of this file reflects this initial declaration, we can be sure the file is free and redistributable. At this moment you may ask, well, what is it good for? The content of this file is a completely random mishmash of ones and zeros. Now, that is true, but we can precisely tell that this is a free and redistributable mishmash of ones and zeros. And that is the key to create the data storage into which everybody can save anything without legal consequences. Let me show you how. First step in the multidimensionalization procedure is to take the original file, it can be copyrighted content or just a regular file, and to transform its binary stream into the sequence of 2-bit numbers. The XOR operation for 2-bit numbers plays a key role here. For example, 2 XOR 1 is 3, 3 XOR 2 is 1, etc. So we take the original file represented by the sequence of 2-bit numbers, up here. Next, let's have this setup of a binary casino. Sometimes I will refer to it as a fission core or just a core. And as you can see, this binary casino contains 3 dimensions represented here by the 3 colors: red, green, and blue. Since we have 3 dimensions, it means the original file will be split into 3 fragments. First, we initialize the counters for each dimension, and then we allow 3 players to enter the casino and let each of them choose a number from 0 to 255. After that, we write the name of the players and numbers they choose in a hexadecimal format. This completes the initial setup and we are ready to go. We will take the first 2-bit number from the original file, and the croupier will select the very first card for each player on the tables in the first row. On the red table it is card V, on the green table it is D, and on the blue table it is R. And now crazy thing happens. All 3 players start talking one to each other, trying to solve a simple yet sometimes tricky math problem. They will try to find a set of numbers on their cards which, when combined by the XOR operation, will produce the 2-bit number from the original file. In addition, they should consider the current state of their counters to avoid reaching 0. So how do they do that? Well, the solution is straightforward. Before the game starts, they will create a lookup table. Basically a handbook containing all the combinations of all cards that can be drawn on each row of the tables, and for each combination they compute a solution telling which numbers on those cards should be selected to successfully fission any input 2-bit number. In our case, only one option is available for combination of cards V, D, R, and the value 0 from the original file. On the V card we must select number 2, on the C card the number 1, because 2 XOR 1 is 3, and on the R card the number 3 is the only option, because 3 XOR 3 is 0. That's it, we can write down the outcome of the very first round, update counters and move on to the next table. You should also notice that some combinations of cards allow players to split a number from the original file in multiple ways. In such case, players literally roll a dice and randomly choose one option. On the other hand, there are also cases where the selected combination of cards does not have any solution. If that happens, players must rewind the time, go 1 or more rounds back to the past and try another approach. This is well illustrated in the following video, where the original file is split into 3 dimensions. I would rather stop the video right now and explain what is going on here. On the left, in this column, there are the 2-bit numbers from the original file. You can see the individual bits nicely lined up here. Then we have all 3 dimensions, all 3 players, red, green and blue, side by side. The header contains the current state of each counter. Seed is the hexadecimal number from 0 to 255 the player has chosen before the first move. Then we have the current hash from the hash algorithm. In this case, it is the output from SHA-3 256, but I am still experimenting with others. The DIMS vector shows the individual cards the player has on a table, and the yellow card is the card selected by the croupier. The number the player has chosen is highlighted in green. Numbers or options that would also work but were not selected are highlighted in yellow. Numbers that cannot be used are highlighted using red color. In the bottom right corner you will find rather important metrics. The collisions counts tells us how often players went back in time because one or more of them either ran out of luck and their counters fell down to zero, or the selected cards of all players did not offer a solution to properly fission a value from the original file, so they need to go back and play the game differently to outsmart the entropy. The bits count here shows how many bits of the original file were already processed, and collisions per bit indicates how many times on average players had to go back to split one bit of the original file. Generally, the golden rule is to have a collision rate between 10 and 100. One important note, please ignore the end card here. It's just a visualization anchor. It tells the rendering algorithm that the seed of all players was updated and there is a need to redraw the screen. So let me play the video again, and you can see how the original file is nicely split into 3 fragments. Sometimes the algorithm goes back, sometimes it goes forward, but eventually it will split the original file into 3 fragments. And when talking about time, you may wonder how long it takes to split 100 MB of data into 3 fragments. Well, it takes tens of seconds when using GPU. However, reversing the operation to fuse fragments together and retrieve the original file can be done without GPU in a blink of an eye. So the splitting procedure is the most time-consuming. Now you must be asking, how do we know that such a fission core or binary casino can split any file? And that is what the next chapter is all about.